Hello everyone, how are you? We have how many people? 50 people already. Great. Okay, I hope everything is good on your side. At least here in Vancouver we have a sunny day, which is great. So yeah, I hope everybody's having a nice day. Okay, so let's start. We have a lot of things to cover today. Uh, yeah, so learning goals. So our learning goals for today are the following. Basically, we need to understand how transformations behave. You will understand why, what I mean with that. That lead us to the actual topic for today, that is composite transformations. I am also show you an example from theory 2 that is actually very related with this. This is the thing that I wanted to show you last time, but we didn't have time. I told you that I was probably going to have an extra video, but because I need that information for the explanation for today, I decided to put it today. And then I will show you a little bit of your transformation assignment. And yeah, but first I need to tell you something very, very important regarding the first coding assignment, the intro assignment. So give me a second. Okay, so if you go to the website, and by the way, we have the PDF from today is already there also, right? So the due date for the intro assignment, right, was this Friday, right? The thing is, I gave you an extra late day. I think many people is probably forgetting about that. So I said that on our first, yeah, people say, oh my God, thank you. Yeah, I think everybody was just forgetting about that. I told you that on our first lecture. So remember that we basically sacrificed the first day of our lectures, right? Because we had this strike. So because we sacrificed one day, I gave you an extra late date, okay? But remind something, please. Okay, many people is saying thank you, you're welcome. So, and the nice thing about that is, remember that late days, we don't count late days, sorry, we don't count weekend days, right? It means that originally the due date was on Friday, right? So an extra late date, it means that now the due date is on Monday, okay? So I've updated that on the website, so it's already all. So on the website you see, right, is Monday, October 5th. So this is already with your late day, right, instead of the Friday, okay? So this is super, super important. And the thing is, I gave you an extra day, late day only for this assignment, right? So in the end, is not using it is just stupid. So yes, so take it, okay? So it doesn't affect the grace day. Well, it doesn't affect your other 3 late days, right? So you still have your 3 late days for the entire term, and you can distribute those wherever you want. But this one was exclusively for this assignment because we lost one day because of the strike. Okay? So yeah, due is next Monday. Okay, good. So let's keep talking about the presentation today. And okay, and somebody is putting a lot of stuff in chat. Okay, good. So from now on, I will, again, remember, I will not see in the chat unless it's necessary or unless I'm asking you something. So if we have questions, I will have several pauses on this lecture for questions. Hopefully it is by raising hand and with audio. Yes, unless I said that you need to use the chat. Okay, perfect. So let's start. So what we have right now is that instead of having 3x3 matrices, now we have these augmented matrices that are basically 4x4, right? So let's just do a very quick recap of that. So this is our original coordinate frame, now in this 4x4 version or affine version, right? So this is basically the identity one. So this is my, again, my original coordinate frame in which I don't have any transformation whatsoever, right? Good. And again, similar to like 2 lectures ago, only for visualization purposes, I'm showing the image in 2D, but we are still in 3D space. And this blue dot here basically represents this basis vector, right? The k basis vector if it's I, j, k, or x, y, z in that case, right? In this case, it's z. Good. So again, this is just a quick recap of the same transformations now in this affine version. So this is a reflection example, but just in the affine version, right? So remember, is the last column we have 0, 0, 0, 1, and the last row is basically 0, 0, 0, 1. Again, exclusively for a reflection example, right? And then we have, in a second, we have scale or uniform scale in this case. Again, just the version with 4x4. Rotation, right? So the linear transformation is in this section here, and we have these extra columns and extra rows. This is an example of shear. Remember, it's also called skew or transvection. Nobody uses that term. Okay. And now we have translation, right? So this is new, right? Because we are using affine transformations, transformation matrices, and now they are 4x4. Now we can include translation here, right? So we can say that we can include, for example, ABC. We can say that the X, Y, Z values for translation, we can call it ABC, and they need to be here, right? So now this is the translation matrix that we can work with, okay? And this lead us to something related with the notation. So remember, this is super important. The notation is very important. All the matrices that I show in this in our lectures are they follow the column notation, right? That is the one that is used by OpenGL, right? It's the only reason I'm using those. Yeah, sometimes it's maybe easier to show row notation, but I'm usually use a column because it's the one that is used by OpenGL. There's the row notation, right? So we are using column notation, but there's a row notation that is used by DirectX, right? And there are differences, right? So as you can see, the matrix is actually different. So in the case of this matrix, for example, sorry. Sorry. So in case of this matrix has two things, right? It has translation, ABC, and it has rotation, right? So it has a rotation component here. So as you can see, the rotation part, the difference with the row notation is that basically you are seeing the transpose, or in this case, the transpose and the inverse of this square matrix, right? This orthogonal square matrix, which is a rotation matrix. And it means that because it's transposed, now the translation is on this section here, right? And in terms of using these matrices, if a matrix has a column notation, it's and you want to multiply that matrix times a vector, is the matrix times the vector, right? So the matrix is on the left side and the vector is on the right side, and the vector needs to be a column vector, right? I think I include this thing on I think on the first quiz, if I remember correctly. Yeah, so there was a question, it was kind of like tricky, and it was basically related with this, right? So you need to understand which is the notation you need. And if you're using the row notation, right, the way you multiply your matrix is different, right? In this case, the matrix is on the right side, so it's the vector times the matrix, right? And again, this is very important for the topic that we are going to see today, which is composing transformations, and is probably the reason of, I don't know, maybe 20% of all the errors I've seen with students regarding assignments, that you just go to a website and see, and you're grabbing or copying things from a website or from code from other person or whatever, and you're just mixing row notation matrices with column notation matrices, and you're multiplying everything together in different order, and everything just go crazy. And those are the errors that are incredibly difficult to debug, because for each specific matrix, you might be totally convinced that, I don't know, maybe imagine that you are composing you are multiplying several matrices, right? And you get the first matrix from a book, and the second matrix from, I don't know, from another book, and the third matrix from another website, and you're kind of combined, right? and you're completely sure for each matrix that they are actually correct. But they can have different notations, and you can actually multiply them in different order. So it is incredibly hard to to find out what is the problem, right? Because in the end, the result could be super crazy. So please, yeah, keep this in mind, because this just makes a lot of headaches. Okay, good. So first, small break for questions. So somebody has a question regarding this? You can use the chat in this case. So say yes if you understand basically what I've said. Okay, somebody is asking something. Okay, again, you will specify if we are calculating on row column notation, right? That's a good question, Tommy. Yes. So again, yeah, unless I say something different, we will always use column notation. Okay. The thing here is, for example, in a midterm, it can happen, or it is possible that in the midterm, maybe in the wording of a midterm, or in the wording of a theory assignment, for example, maybe in the words, we can maybe write vectors as row vectors, because that is like, it's more compact to write in a sentence, right? But if we are asking you to perform operations and we are showing matrices, or we are asking you to perform matrices, we're always assume that we are talking about column vectors and obviously column matrices, right? So please use column matrices and column vectors for all lectures, all assignments, everything, except if we say something different, right? Okay, so Drew is asking, if the zeros at the bottom row had other values, subsequent translation would get really weird. Yes, because for the element, yes, exactly. So that is a very good observation. So if I come back, this last row, right, in the case of column rotation, or the last column in the case of row notation, right, this should be 0, 0, 0, and 1. So please never put a different number in these things, right? So yeah, things can get very weird if you put another number. This is maybe not as, I don't remember right now if I've seen this problem before. Maybe it's not as common, but yeah. And then it's a typo, right? So maybe you're creating your matrix in JavaScript and you just, yeah, made a mistake and you put a different number here. You can get very weird results, right? Okay. So any important question that you want to raise your hand, or can I keep going? Okay, Ken is asking, what will show if there is a 10 degree in the linear transfer matrix? I don't understand your question, Ken. So maybe computer explode. Okay, let's continue, and maybe you can raise your hand later on the lecture, and maybe you can ask your question later. Okay, good. So let's continue. So what is this transformation composition? It means that affine transformations can be combined into one single matrix by multiplying those matrices. This is super important, and this is possible because we are using affine transformations, right? So if we use, for example, 3x3 matrices, you can also combine 3x3 matrices. You can have, for example, two rotation matrices, 3x3, and you can multiply them. The thing is, because we needed to add translations, right? The beauty of this, and the nicest thing about having an affine transformation matrix, is that you can have, in the same matrix, you can have rotations, scaling, shear, whatever you want, and also translation, and you can multiply everything, and you can get a single matrix that basically contains a lot of transformations combined, right? And you never lose your translation, because it's handled by these extra rows and extra columns, right? But first, before seeing how you can actually multiply those matrices, let's talk about how transformations actually behave. So this is related with your theory assignment, your theory 2 assignment. So this is what I wanted to show you on our last lecture. So this is an example that is very similar to your theory assignment. And again, maybe some of you already know how to solve this, but in my experience, a lot of people is usually confused by this topic in particular. Okay, so let's see. Again, this is similar to the theory assignment. So we have two coordinate frames, A and B, and they have obviously a different basis vectors, and we have a point P and also a vector V. Okay, so let's say that we want to compute the position of P with respect to V. Okay, and again, sometimes it's very easy to see the solution with the grid, right? So can you tell me what is the answer? So Nami is saying 2, 2. Does everybody agree with Nam? That is 2, 2? Yes. Yes, exactly, 2, 2. So we need to walk 2 times the basis vector I and 2 times the basis vector j, and we get to P, right? Perfect, that is nice. Okay, it's very easy, it's very straightforward, because we have a grid and this kind of makes sense, right? And it's not only because we have a grid, it's also because the position of P is very convenient for me right now, because it actually, it's a very easy one to see with the grid, because the position of P. But now let's say that we have another position, which is Q, is in this position. So just by seeing the grid, can you guess which is the position of Q with respect to B? Just by seeing the grid, it is possible. What do you think? Again, here I'm seeing the chat. Okay, Danny is guessing 1.51. Okay. Tommy is saying you gotta skew it. Okay. 0.75, 1. So Gloria is 0.75, 1.25. Yeah. So see, nobody is. I mean, not everybody is agreeing, right? So it's not that easy anymore, right? So in this case, in the case that the grid is not enough, right? So we need to actually compute with numbers, compute it with numbers. And by the way, let me tell you something that is also super important. Either on theory assignments or midterms or final exam, if you have a question like this one, and you can actually compute the position only by seeing the grid, you can put that as your answer and that will be okay. Okay? So please keep that in mind. So in general terms, in midterms and exams, if you have a question that, if you're doing an exam, right, or a midterm, and you have a question and it seems that you need to make like a super sophisticated or very long computation, right? You're probably doing the wrong way, right? So always try the easiest way before, right? So, and again, if you can use the grid and you can just give the solution just by seeing the grid, that is perfectly correct, either for theory assignments or a midterm or a final exam, okay? But in this case, it's not possible to use the grid. So how we need to compute this? So as everybody probably already knows, sorry, I'm coming back, sorry. As probably many people already knows, we need to do this, right? So you need to use the inverse of the matrix of the coordinate frame B. So what is this matrix, right? So we already talked about this. This matrix, right? The matrix of the coordinate frame B is basically composed by the basis vectors of the coordinate frame B, I and J, right? And we need to take the inverse of that, right? And then multiply by the coordinates of the point Q with respect to the coordinate A, right? So this is basically what we have, right? Again, this is the basis vector I with respect to coordinate A. This is a basis vector J with respect to coordinate A. And this is basically the coordinates of the Q point with respect to coordinate A, Everybody agrees with this? This is the part that can be confusing, right? Because it's okay, what is happening here? Why? I'm telling you that this is the coordinate position. These are the coordinates from the point Q with respect to coordinate A. And I'm telling you that is 2, 0, right? And many people is already saying, Nam is saying, and yeah, maybe a lot of people is saying, hey, wait a minute. So isn't the coordinates of Q is 4, 4, right? Because Q is actually in this position and A is in this position, right? So it should be 1, 2, 3, 4, 1, 2, 3, 4, right? So if you agree that this is kind of confusing and it seems that the position of Q is actually 4, 4, say yes. If you agree that it's confusing. Yeah, see, it is confusing. It is confusing for many people. Okay, so let me tell you what is happening here. Where are these numbers come from? So the thing is, whenever you're dealing with coordinate frames, remember, a coordinate frame is just a collection of basis vectors, right? And remember, vectors and points, they both use the same data, right? But they're different things, they're different animals, right? So vectors define a direction with a magnitude. And vectors have associated basically two points, right? One is the origin of the vector, and the other is basically the tip of the vector, right? But because we always use the same data, can you tell me which is the origin, the actual origin for all possible vectors that we use in computer graphics? Which is the origin for all vectors? Yeah, but which one? Yeah, so Gloria is saying same. Can is saying no. Yes, 0, 0, 0. Every single vector starts in 0, 0, 0. So the thing is, when you're dealing with coordinate frames, you need to assume that the coordinate frames have exactly the same origin. Okay? This is super, super important, because what you're dealing with is you're dealing with vectors, right? So let's see what is happening here. When I tell you that this column vector here needs to be the coordinates of the basis vector I from B, right? So this is vector I from B. You agree? Okay? So these need to be the coordinate frames of this vector with respect to A. Okay? When I said the coordinates of a vector, I mean the coordinates of the tip of the vector. You agree? So the tip of the vector is this point here, right? So this is the vector, right? But if I want to get the coordinates of this vector with respect to A, because this is a vector, this vector actually starts in 0, 0, 0, in the origin of, in this case, A. So you need to kind of move this vector into this position here and compute its coordinates, and its coordinates will be 1, minus 2. Or you can do something different, conceptually different, that is basically like assuming that you are taking the coordinate frame A and moving A on top of B. And now B is success, and B and A now they have the same origin. If you do that, if you imagine that in your head, now you can compute the actual coordinates from your basis vector I, right? So the basis vector I from B is here, right? This is the tip. Can you see my mouse, by the way? Say yes if you can see my mouse. Okay, perfect. So this is the tip, right? So this is the coordinate with respect to A with the same origin. These are the coordinates 1, minus 2. This is 1, minus 2, right? Good. Now let's see what happens with the other column vector. The other column vector is the tip of the basis vector J from B with respect to coordinate frame A, right? But again, assuming that they all start on the same origin, right? So this is the tip, the coordinate is 1, 1. This is 1, 1. Yep. And we need to multiply, well, we need to take the inverse of that thing, the inverse of that matrix, and we need to multiply that times the coordinates of this point Q with respect to A. And again, in this case, it is what we have is a point, but now is the moment in which we can kind of um, um, use vectors and points kind of like almost as the same creature, kind of, because in this case we need to treat Q as a vector, because the position of Q now is this vector here, right? And again, this vector, because it is a vector, it needs to start in the same origin, right? So what is the coordinates of Q with respect to this, to A on the same origin than B, is 2, 0, right? So that's how you actually construct the matrix. Okay? Okay, good. So same thing happens with vectors. So this is something similar to what I am asking you on your theory assignment. You have a vector, in this case is vector v, for example, and the vector is drawn in a different position on the grid, right? And I can ask you, for example, what are the coordinates of the vector v with respect to b, right? So in this case, it's the same, because this guy is a vector. And remember, conceptually, we can draw vectors on any place on this Euclidean space. You can see in many books or whatever, you can see vectors drawn in different places. But you need to understand that vectors always start in the origin, right? So in this case, what you need to do is take vector v and basically translate that one, or imagine that that vector is basically on the same origin as v, right? And taking its coordinates with respect to a, but again, imagine that a is actually on the same origin. So can you tell me what are the coordinates of vector v with respect to coordinate frame a, if we want to do this translation? Can you tell me the coordinates in the chat from vector v? 2 minus 1, exactly, right? So if a would be here, for example, or if this vector b would be here, this will be the tip of the vector, and it's basically 1, 2, minus 1. Good, perfect, nice. So again, another break. Is this clear for you? Can you say yes if it's clear? Ish, okay. My hand is up. Okay, perfect. Let me. I didn't see the hands. Yes, Nam, you can talk.
Hello.
Hello.
Okay, so let's go back to the previous slide. And suppose coordinate frame B is the camera and coordinate frame A is the world.
Yeah.
Then if you wanted to get the world coordinate of point Q, then shouldn't you take the translation between A and B into account? Then we're implicitly assuming translation doesn't matter, but obviously if you're thinking about world and camera, it does. So what's the case? What's the deal here?
I would like to. Okay, that is a good observation. Yes. The thing is, I'm not talking about translation here, right? Because we are just directly. We want to just directly take the coordinates regarding a coordinate frame. So yeah, let me think about it. If this, yeah, because I will talk about that actually in a couple of minutes. So translation is important, right? But for this question in particular, as is the wording of this question in the theory assignment, and for this thing in particular, we are not dealing with translations yet. So in real world, or in, yeah, when we actually compose everything with the world coordinates and everything, yeah, the position of the camera is important for sure, right? But yeah, can you wait a little bit? Maybe I will answer that on the next sections. Is that okay, Nam?
Yep.
Good, perfect. Yeah, but for now, again, yeah, we need to assume that they are in the same origin. Okay, so Pavel, I can hear you, Pavel.
Yeah, can you go another slide back?
This one?
Where you superimpose the two. Yeah. So I was just wondering why are we saying to get the direction in with respect to A? Because if we just think in respect to B, and the I and J vector would be the same, right? if we just think about I vector with respect to B, it's still 1 minus 2. Why are we thinking it in respect to A?
Why? Okay, so why, when constructing the transformation matrix, why we take the coordinates from each of these basis vectors with respect to A? That is what you were asking?
Mm-hmm.
Because we are basically translating from one coordinate frame to another.
Okay.
Right?
So we're going from A to B?
In this case, we're going from A to B, exactly.
Okay.
Yeah.
Okay. Thanks.
Okay. Then Doruk.
Hello.
Hello.
How would the answer for QB change if A was scaled by 2 or any number?
Okay, that is a very good question. The thing is, in this case, the first coordinate frame that we are like taking into account, in this case A, it's like it's like, how can I say this? If you say that the coordinate frame A is scaled by 2, right? Instead of that, the way you need to understand the way you need to compute that is not by taking the coordinate A and scale it by 2, because coordinate A will be always 1 1. So in this case, the coordinate A, or your original coordinate frame, is not scaled, is not rotated, is the actual word, right? So if you want to scale coordinate A 2 times, it means that instead of that, you need to imagine that coordinate B is shrinked by half.
Okay, I see.
Yeah.
I see.
Because
Right.
whenever you do this type of translations, at least one of those coordinate frames needs to be an original frame that has absolutely no transformations, right? So always, you always need to get something as a reference, right? So your reference must have no transformation whatsoever, right? Something that can happen, that actually happens on your theory assignment, and I'm not showing this right now, is in your theory assignment. I don't know if everybody already opened the PDF, but in your theory assignment, you have different coordinate frames. You have several coordinate frames. So you have a coordinate frame A, which is like the original coordinate frame that has no transformations whatsoever. So it basically is the one that is the same as the grid, right? So the word is the grid, and the coordinate frame is basically the same as the grid. So it has no translation, no transformations, no rotations, no nothing. Okay. So, and then on the assignments, if I remember correctly, I am giving you 3 different coordinate frames. So I'm giving you like B, C, and D, right? What I can ask you, for example, is to create a transformation matrix that goes from coordinate B, which has some type of transformation, to coordinate C, which also has some different transformation. So in that case, what you do, right, is, because you usually need to have something without transformation to rely on, right? Like an original coordinate frame. Imagine that you have another weird coordinate frame here, right? That is coordinate frame C. And I want you to create a matrix to transform from B to C. Directly, it will be very hard. So what you usually do is you first create a transformation that goes from B to A, then you create another transformation that goes from A to C, right? And then now you have 2 matrices. One matrix translates from B to A, and another translates from A to B. You multiply those together, and now you have a new matrix that basically translates from B to C. Okay?
Okay.
That is exactly what you need to do on your assignment, right? And again, it is obviously possible to directly compute a matrix transformation from a weird coordinate frame to another weird coordinate frame, but it will be incredibly hard, right? Because you'd have nothing to grab, right? You have nothing sane to take these coordinates to create these matrices. Okay?
Okay.
Good.
Thank you.
Perfect. Okay, so I think it's only David. Okay, unmute. Yeah, David, I can hear you.
Hi. Yeah, I have a question on this page about like when do we use the inverse matrix here? Because I remember when we first introduced, we don't use this, right?
Sorry, what do you mean? We were not
I mean
using
in
in the previous
the
lecture?
past slides, I remember we did a similar problem without using the inverse matrix, right?
No. We did. If you
We
go
did?
back, yes, if you go back to those slides, you will see that basically, if we are talking about translating from A to B, right? You basically have two possible directions. Either you translate from A to B, or you either translate from B to A, right? So in one way, in one direction, you use the matrix without the inverse, right? You just multiply
Yeah.
the matrix times the vector. And in the other way around, you use the inverse of the matrix. So if you go back to those slides, you will see that in one direction you use the matrix, in the other direction you use the inverse. So yeah,
Yeah, that's why it's confusing. Why can we only use the like in one direction? Can we just assume like they're I mean
well, okay.
it's the position is relevant, right? We can just assume they're like each other and we don't use the
Yes,
inverse.
but
I'm not sure.
I agree. But the thing is, in real life, in computer graphics, sometimes you do need to go in one direction. Sometimes you do need to go in the other direction, right? In the other way around. So yeah, that's why you need to sometimes, as this one, you need to use the inverse of the image.
But so for this one, is it possible to do it without inverse, or do we have to use inverse?
For this specific question that I'm showing here, you need to use the inverse of the matrix. But I'm also show you today another way to solve this without taking the inverse of the matrix. I
Okay.
will show you that today. Yeah, but
Okay.
it is a good question, of course, because yeah, every time we we hear inverse matrices can be yeah hard, right?
Yeah.
Good. But yeah, I will show you another way. Okay, so now Tommy.
Hi.
Hello.
I feel like you answered this question already, but I'm not really sure what inversing the matrix here does. So when we're inversing, which I imagine this matrix is B, do we go back to, are we transforming from B to A basically?
Okay, maybe the yeah. I think I'm already explained that, but what I can say is always remember this: for any transformation matrix, right? Any matrix like this, they represent a transformation, right? So they represent either rotation, scaling, something, right? You're taking a point that it was originally in a grid in a certain world with a certain coordinates, and you just like distorting that world, right? So that is a transformation. So the inverse of a transformation is like playing back that transformation, right? It's only that. So that is why when you want to translate from one direction to the other, you use the actual matrix. When you go to the other side, you use the inverse of the matrix, right? In this case,
Oh, I
the
see.
way
Okay.
I'm framing the question, right? In this case, the way I'm framing the question is you need to use the inverse of the matrix, right?
Right, because A is like our starting vertex without any transformations applied, whereas B is like applying transformations onto A, which is why
Yes.
we're
So
taking
for
the
example,
inverse. Okay.
yes. So for example,
Okay,
let's
that makes sense
let's
now.
imagine that the question is different. It has different wording. Let's imagine that now I'm saying I have point P with respect to A, right? Really with respect to A. So in that case, point P will be 1, 2, 3, 4, 5, 6, 2. Okay? So point P with respect to A
Right.
will be 6, 2. Okay. Now I am asking you what is the transform version of P by applying transformation B. So right? So I want to apply
Right.
the transformation of B, or the coordinate frame B. I want to apply it as a transformation. Now in that case, I get the same matrix without the inverse, and I just multiply by P, and what I will get is that now I mean, as you can see, for example, I is kind of like rotated and scaled version of I, right? The I from B is kind of like rotated and scale, and J is also kind of like a rotated version. So in this case, P will be probably like going down there, right? I mean, in a maybe in that position similar to here, probably, right, where my mouse is. In that case,
Right,
you don't
right.
need to use the matrix, right? But in this case, I'm asking the other way around, right? Okay, good. So yeah, so I think yeah, okay. So we don't have anyone with raised hands. Perfect. So let me keep going. Okay, so let's see. So imagine that I have something like this. I need to rotate this bunny, right, around the point P by 35 degrees. Okay, so what happens is if I just take a transformation matrix, in this case a rotation matrix, and I apply a transformation matrix with 35 degrees, this is what will happen, right? Because rotation matrices or transformation matrices, they are always they always have the same origin. In this case, if I rotate something, rotation is always keeping the center fixed, right? That is why they are linear transformations. Remember that is part of the actual formal definition of a linear transformation. And a linear transformation always leaves the origin fixed, right? So I'm not rotating, in that case, I'm not rotating around P. I'm rotating around the origin. I'm always rotating around the origin, right? Because it's a transformation matrix, it's linear, and it will always keep the origin fixed, right? So this is clearly wrong, right? So can you guess what would be the solution if what I want is to rotate this bunny with two heads 35 degrees with respect to P? What do you think? So Drew is saying translate. Yes. So what we usually do, thanks Drew, is you first need to translate the bunny to the origin. So basically taking the coordinate frame from point P, you basically translate the bunny to the origin, right? Then you rotate the bunny, and then you take the bunny back to point P. So you translate, rotate, and then translate again. And that is exactly what we call a transformation composition or composite transformation. Basically, you have something like this, right? Again, because we are using column vectors, this is the column vector for all positions on this bunny. And you first need to translate with the coordinates from P, right? So translate back. So you have one transformation matrix with your translation, another transformation matrix with, in this case, a rotation with 35 degrees, and then you translate back. What was QB? Sorry, I don't understand the question. Someone is asking, what is QB? Oh, okay. If you're keep making questions regarding the past slides, yeah, I mean, I think I'm already explained that, and you can also check the video later, right? Okay, but let's keep here. So is this clear, right? You need to basically perform different transformations and basically compose everything by multiplying those matrices. And something that is super important again, and this is because we are using column vector notation, is the order of operations is from right to left. So the first operation is the one that is the rightmost. So this is the first one, the second, and the third one, right? This is super important. So the idea of composing transformation or composing transformation, if we can make a recipe, is that we usually first translate the geometry to the coordinate frame in which the operation is simpler, right? So again, in this case, we have a 3D world in which we have this bunny, right? So the bunny has its own coordinate frame, but now the bunny is probably translated, right? So we first take the model, the points, or whatever we wanted to transform to a coordinate frame in which the operation is simpler. Then we apply the operation we want, either scale, rotation, or whatever, and we finally translate the geometry back to the original coordinate frame, right? So that is basically like the recipe for composing transformations. And there are basically like two flavors of the same recipe. You can do that with respect to the object, which is basically like this animation here, in which you take the object, you translate the object to the origin, then you apply the rotation and you get the object back. Okay. And another version, which is probably weird for you, but is sometimes we use it, is instead of applying this composition with respect to the object, we can also apply it with respect to the coordinate frame. So in this animation is the opposite. We get the origin of the world, we translate it to the point P, and then we rotate the world and we get the new transformation. This is something that sometimes we actually do. Sometimes it's easier to, instead of moving the objects on a 3D world, it's sometimes easier to move the world. That is, so Tommy is saying that was some spooky stuff. Yes, it is spooky, but it's actually sometimes it's actually better. This is what actually happens when we transform the camera, okay? Because we are not moving the camera with respect to the world. When we finally get the transformation from the camera, what we are actually doing is we are moving the world with respect to the camera instead of moving the camera with respect to the world. Okay, so that leads us to the composition of the coordinate frames on a scene, and this is related with what I think Nam was asking about. So if I have a scene like this one, right? This bunny right here, imagine that this is an OBJ file, right? Exactly as the one that you're working right now with your intro assignment. You have the raccoon, and raccoon is an OBJ file, and if you open that file in whatever program you want, you can see coordinates from all those points, right? So it means that this model right here, or the raccoon, it has its own coordinate frame, right? All the positions of the bunny, they have an orientation or a position with respect to a 0, 0, 0 of that OBJ file, right? And which means that once you move and rotate that bunny, right? So for example, inside your JavaScript, you can take that object and move that object, right? And now you have a world that it also has a coordinate frame, which in this case is called view matrix. So usually this matrix, the matrix of the object, is called model matrix, and the one from the world is called view matrix, right? And you also have a camera, and the camera has also its own matrix, its own coordinate frame that is called projection matrix, right? So you have basically three things: the model matrix, the view matrix, and the projection matrix. That is exactly what you see on a vertex shader. So this is the example that I've show you many times, in which you can see that we have the actual positions, the original positions from your objects. They're multiplied by this matrix, which is model view matrix. This basically has the transformation from the model view from the model matrix to the actually view matrix, basically with the world coordinates. And then you multiply everything, well, you multiply this one times the projection matrix. So remember, the order is always, because we are using columns, is always right to left, right? So this is exactly what you're seeing in your vertex shader. And finally, because I still have like 2 minutes, so let me show you, I promise you that I wanted to show you a different way to compute this without making an inverse matrix. And this is super important because, again, if you have a midterm or a final exam and you have a big matrix and you need to take the inverse of that matrix, and you will say, oh my god, this will take a lot of time, and that will probably consume 20% of your time. You're probably doing the wrong way. Okay, so there are other options. Okay. And Tommy is saying, just don't give us that question then. No, you need to have those types of questions. You need to think about it. Okay, but yeah, good comment, Tommy. It was very fun. Okay, so let's come back to the same question, right? I need to get the coordinates of point Q with respect to coordinate frame B, and as we said, what I need to do is basically take the basis vector I and j with respect to A, right? and multiply by the coordinates from the point Q with respect to it. And we already see that we need to assume that the origin is the same, blah, 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 blah. Okay. The other way to solve this is by solve it as a linear combination of the basis vectors. Because it's like having, say, okay, this is exactly the same as having a basis vector I and a basis vector j multiplied by scalars, right? So basically you have a scalar that multiplies this vector plus another scalar that multiplies this vector, and that gives you this position here, right? And again, this position is the same as this thing, right? So if you solve it like that, you basically have these two beautiful equations, and then it's super easy to compute this, right? Once you solve this linear system of equations, you basically get these results. Alpha is equal to 2/3 and beta is equal to 4/3. And I think somebody already put those things on the chat, so maybe you got it right. And this is the solution, basically. Yeah, these are the solutions. These are basically your x, y values for these basis vectors, right? In this case, I'm just calling them alpha and beta. And this is exactly the same result as if you take the inverse. So if you take the original matrix and you get the inverse, this is the inverse of that matrix. And if you get that multiplication, you will get exactly the same result, 2/3 and 4/3. So depending on the numbers that you have, sometimes it will be easier to actually compute the inverse. Sometimes it will be easier to compute it as a linear system. So can somebody tell me an example of in which circumstance would be very easy to compute the inverse of this matrix? Can you tell me in which circumstance? Yeah, okay, the identity, of course, that thank you, Nam, but that is extremely easy. Okay, another one. Yes, thank you, William. Orthogonal. What happens, William, if this matrix is orthogonal? What is the inverse of a orthogonal matrix? The transpose, of course. And which means that if this matrix, for example, is a rotation, right? If it's a rotation, rotations are always orthogonal, which means that the inverse of a rotation matrix is just its transpose, right? So that's why you need to understand all these things and to be very clever to observe what we are asking, right? Because if suddenly what you have there is just a rotation, taking the inverse is super fast, and maybe that is the fastest way to get the answer. If not, maybe you need to express it as a linear combination, and then it will be faster, right? Okay, and that's it. Yeah, that's it. So next lecture we will see forward kinematics, forward and inverse kinematics, and yeah, thank you so much, everybody. See you on Friday.